In this video, we are going to continue talking about the topics in chapter 3. Now we are going to be focusing on amino acids and how they act as acids and as bases. One of the things that we already established is that when we look at the structure of amino acids, they contain a carboxylic acid and they contain an amino group. Now, one of the interesting things is that when amino acids are placed under different pH conditions, they become ionized. So understand that at pH of 7, and we already learned that pH of 7 is neutral pH, one of the things that is observed is that amino acids have a 0 net charge. Because what happens is that when we are at pH 7, the overall structure of an amino acid specifically illustrates that your carboxylic acid in your amino acid has lost a proton. So it forms a carboxylate. Okay. Now, interestingly, under those conditions, if we look at the amino side, at the amine side of a carboxylic acid, it is actually protonated. So, what does this mean in terms of the amino acids themselves? Well, that if we fluctuate away from pH 7, either way, going into low pH or going into really high pH, we are going to see changes at the level of the structure of the amino acids, specifically how the carboxylate and the amino side are going to change. Now, one of the things is to remind you, because amino acids can act as acids and bases, that means that they are, similar to what we saw in water, amphoteric. So remember, the term amphoteric refers to substances or molecules that can act as acids or bases. Now, understand that what happens overall is that if we look at the structure of an amino acid when it is at low pH, let's say that it is around pHs that is going to be less or equal to 2. One of the things that it is observed is that because the pH is so low and we have protons available, we see overall that our structure is going to specifically illustrate that our carboxylate portion of our amino acid is going to be protonated. Now, how does this change the net charge in the amino acid? We observe that at pHs lower or equal to 2, the overall charge, the net charge of the amino acid is positive 1. So now, what if we go to the other extreme? Meaning that now we're going to be at pHs that are really high. Let's say that we are now talking about pHs that are going to be higher or equal to 10. Well, because now under those conditions, since we have a higher concentration of hydroxide, because remember, at higher pHs, we are going to have more hydroxide available. Understand that what's going to be happening overall is that our amino acid is going to be -1 charge, because not only we have lost the proton in the carboxylic acid, but also the ammonium that it is produced at pH 7 is going to be deprotonated. So our amino side, which was protonated, now it becomes deprotonated and it is neutral. That's where the -1 results for. So what does this mean overall? That at pH 7, you see that the molecule is 0 net charge. That is specifically known as the Zwitter-ion form for an amino acid. If we are at pHs lower and equal to 2, then we have a cation version for our amino acid. And as we get into really high pHs, 10 or above, then we have the anion version of our amino acid. Now, understand that these different forms of the carboxylic acid portion of the amino acid, the amino side of the amino acid, and that I have highlighted in these examples comes from the idea of the pKa's that we have for those groups within the amino acids. So you may be asking yourself, why is this important? Well, understand that because we have observed before that molecules that have these properties of acids and bases can undergo in experiments, one of the things that can happen is that we can titrate amino acid. When an amino acid is titrated, of course, there's going to be the resulting curve, which is a titration curve. And in that titration curve, we are going to see specifically how the reaction of the functional groups that are going to be donating protons are going to be changing overall in this titration. So to talk about what happens overall, here on the left side of the slide, we have the titration specifically of the amino acid alanine. One of the things that I want to point out is that this specific trend that I'm illustrating in this titration is going to happen to this amino acid because the side chain, it is not affected by changes in pH. Because remember that, for example, in alanine, the side chain is a methyl group, so changes in pH are not going to be pulling the protons away. The pKa of a alkane is really, really high, is in the 50s. So let's see what happens overall in the titration experiment for alanine. So understand that when we start a titration experiment, we are going to have the particular form of our amino acid. So at the beginning of our titration, understand that what is happening overall is that we are going to have an amino acid, okay, that is going to be overall positively charged. So it's going to be a cation, okay? Understand that here in the x-axis, we are going to have the equivalence of the hydroxides. And remember that as we're moving from left to right, this is going to be increasing in the amount of sodium hydroxide that we're adding. And then on the y-axis, we're tracking what is happening overall to the changes in pH. So, as I was mentioning in the beginning of our titration, the structure of our alanine is going to be a cation because we have the protonated amine group and we have a carboxylic acid. Now, as we increase the amount of sodium hydroxide that it is placed in the container with this amino acid, notice that once we have reached the pK1, which in this case is going to be around 2, what happens overall, and I'm just going to highlight the atom so we can keep track of it, is that once we have reached that pK1, okay, our carboxylic acid loses its proton. So this means that around pH 2, your carboxylic acid will be losing the proton. But this in a way makes sense because if we relate this to the previous slide, we remember that the pKa of that carboxylic acid, it is around 2. So what does this suggest? That as we are increasing the amount of base and we have reached the pH has reached the pKa of your carboxylic acid, then the proton in the carboxylic acid is going to be dissociated and is reacting with the base. So understand that at this point, we have created our Zwitter ion. So the overall charge of our amino acid is 0. As we continue, understand that once we have reached the pK2, and if I And this is not to scale, so forgive me for this. I'm just doing relative numbers. So this is going to be close to 10. I'm just going to round it to 10. So around pH of 10, we see that overall we have reached the pK2. So this pK2 happens to be this pK2 happens to be around pH of 10. If we relate it to the previous slide, then we know that that corresponds to the pKa of the protonated ammonium. What we see overall is that if we keep track of what is happening to our functional groups, our protonated ammonium has lost a proton, now is neutral, so the overall charge of our amino acid is negative. Okay? So, why is all of this important? It is because of the term, let me just highlight it here, of the PI. So you may be wondering, what exactly is the PI? Well, the PI, it is actually defined as the isoelectric point. What is the isoelectric point? Well, it is the pH where the amino acid has no net charge. And you may be wondering, why is this important? When an amino acid has no net charge, it does not move when an electrical current is present. So you may be wondering, wow, okay, so why would that be important? Understand that the isoelectric point, or taking into account the isoelectric point for an amino acid within a peptide or within a protein, it is one of the techniques that it is utilized to isolate or purify peptides and proteins in a particular experiment. Now, the isoelectric point can be calculated. And I'm going to illustrate now how the isoelectric point is calculated depending on the amino acid that we're working with. Let's first look at glycine specifically. As you can see on the left side of the slide, we have the titration experiment for glycine. One of the things that I wanted to illustrate, even though I'm not going to focus on it, remember, your amino acids are going to have that carboxylic acid and that amino group present in them. So looking at the titration curve for them, this clearly illustrates why we have as a buffer system protein systems. If you remember from the previous chapter, we know that one of the buffer systems that exist in the body, it is because of proteins. Well, by looking at this, as you can see, because of the amino acids that are in proteins, we can see that there's actually two buffer regions. But right now, I'm not going to focus on the buffer regions. I'm going to focus on the isoelectric point. So this is the idea. As you can see, in the isoelectric point is where overall I have a net zero charge on my amino acid. So how do I calculate this for an amino acid? Well, as long as your amino acid, its side chain, it is not affected by pH. And you will see it because in table 3.2, in the textbook, you are not going to have a value on RH or RH plus. What you can do is that to calculate the PI, you are going to add the two pKa's, the one for the carboxylic acid and the one for the amino group, and you're going to divide it by 2. So the PI is going to be pretty much the average between the two pKa's. So when I take 2.34 plus 9.60 and we divide it by 2, the result is 5.97. And as you can see here, from the titration experiment that illustrates the PI for glycine, which is where we have the formation of the Zwitter ion. But what happens if your side chain then is affected by the changes in pH? Well, let's look specifically at the example where you have an acidic amino acid. To look at this, we are going to look at the titration curve for aspartic acid. So aspartic acid, or even for glutamic acid, is going to be the same idea, and their PIs is going to be calculated in a similar manner. So understand that when you have an acidic amino acid and we look overall at the titration curve, okay, as the titration is progressing, notice that the first pKa is going to deprotonate. So I'm just going to zoom in so it's a little bit more clear. And I'm going to highlight the atoms that are important. So as the titration is taking place, as you can see, we start with the amino acid that has a carboxylic acid that is protonated. The amino group on the alpha carbon is protonated. The one in the side chain is protonated. So as we add base, notice that what happens to the molecule is that the carboxylic acid that is attached to the alpha carbon is going to lose its proton. Now, understand that once that occurs, that's where we have the zero net charge, our Zwitter ion. Our molecule has a net charge of 0. So what does this mean? That when we're trying to calculate the PI for aspartic acid or also glutamic acid, but what we are going to be doing is that we are going to be taking the average between the pKa of the side chain and the pKa of the alpha carbon. So what does that mean? That when I look at table 3.2, I'm going to utilize this value and this value to calculate the PI. Because as you can see, when the proton from the carboxylic acid at the alpha carbon, I generate my Zwitter ion. So to calculate the PI, that is going to equal 2.09 plus 3.86, and we're going to divide this by 2. Let me just do this mathematical operation. 2.09 plus 3.86 divided by 2. I get a PI of 2.98. But if we look at the titration, look at where the PI is. As you can see, close to 3. Which this explains why we obtain this value. Remember, the isoelectric point is going to be where we have overall a net charge of 0 in a particular amino acid. So if you have to calculate the PI for glutamic acid, is going to be very similar. You're going to take the average of the pKa of the carboxylic acid attached to the alpha carbon plus the pKa of the side chain, which is also a carboxylic acid, and you're going to divide it by 2. So what happens if we have an amino acid that it is basic? Well, let's study what happens overall in lysine. Okay, so lysine is one of your basic amino acids, and as you can see here, this is the titration experiment for lysine. So again, when we start overall the experiment on lysine, we notice, and I'm just going to highlight again the functional groups that we're paying attention to. We're going to highlight the alpha amino and the side chain amino. So when we start our titration, my lysine overall is positive 2. As I start increasing the pH of the system, notice that around pH of 2, what happens, and it's very similar to what we've seen before, I lose the proton on my carboxylic acid. But again, I have not reached a net charge of 0, because overall in this molecule, if I keep track of my charges, my carboxylic acid that is attached to the alpha carbon is -1. My amino next to the alpha carbon is +1. My amino group in the side chain is +1. The overall charge of the molecule is going to be +1. Then I continue increasing the pH in the system. So once I have reached the next pH, okay, in which now a pH value, if I look at the pKa's, is going to be a little bit higher than 9. If we look exactly here, it's going to be around 9. So once I have reached pH of 9, then notice that what I have is that around pH of 9, now I'm losing the proton that was present in the amino group that was next to the alpha carbon. Now, if I keep track of my charges overall in the molecule, this is -1, this is 0, this is +1. Oh, so at this point is where we have created our overall 0 net charge. So what does this mean? That in order to calculate the isoelectric point for positive amino acids, or basic amino acids, I should say, like lysine, like arginine, like histidine, what I am going to be doing is that I'm going to take the average of the pKa on the amino group that is attached to the alpha carbon and the pKa of the side chain amino acid. So what does this mean at this point? That if I go into the values, and again, they are given in table 3.2, for lysine, I'm going to take specifically (8.95, 10.53). So to calculate the PI for it is going to be 8.95 plus 10.53. And when I take these values and divide it by 2, let me just plug it into my calculator. 8.95 plus 10.53, and then I divide it by 2. I see that the PI for this system is around 9.74. So it is close to 10. And as you can see here, and again, I'm just using my calculations, it is close to what we see here, which is the isoelectric point for it. So just understand that the way that you calculate the isoelectric point for a particular amino acid, it depends on the situation that you have. So to review, If you have an amino acid that there is no pKa for the side chain, then understand that the calculation that you're going to be utilizing is the same equation that we use for glycine. If you have acidic amino acids like aspartic acid and glutamic acid, the following equation for the PI is going to be utilized. And lastly, if you have specific amino acid that is basic like lysine, arginine, or histidine, this is the equation that you utilize for the PI. Now, understand that there's going to be these pKs for the 20 common amino acids. And overall, it is important to understand how they are going to look like when they are by themselves or when they are in the context of a peptide or protein. So the general rules is that when the pH is considerably lower than the pKa, we expect both sides, meaning the amino side and the carboxylic acid, to be fully protonated. And as you can see, that is illustrated. I'm just going to highlight it. This means that we're going to have a positive and ammonium for your amino, and we're going to have a carboxylic acid that doesn't have any charge because the bonding pattern for the carboxylic acid. Now, when we raise the pH a few units above the first pKa, okay, understand that as long as we're still way below the second pKa, then what is going to happen overall is that the carboxyl group is going to lose its proton. And as you can see, we can see it illustrated right here. Okay? Here, specifically, if the side chain that you have is not affected by pH, at that point is where we form this Zwitter ion. And as you can see, that is true for many amino acids, but remember, that is not true for amino acids in which the side chain is affected. Lastly, when you raise the pH to well above the amino acid value for the nitrogen, and what I mean with this is the pKa. That second pKa, what happens overall is that the nitrogen will lose its proton. And we can see it reflected right here. Now, when nitrogen loses its proton, it's going to be now, according to the common bonding pattern for nitrogen, it's going to not have a charge. It's not going to be ionized anymore. Okay? Understand that under the first conditions, the overall charge for your amino acid is going to be positive. At this Zwitter ion is going to be zero charge. When we have specifically the last case, we're going to have a net charge of negative. And again, this is when we're looking specifically at the amino acid by itself.